All right. Hello again. Let's go ahead and jump into Explore number 3. I'm going to go ahead and draw my lines here. I'm not sure what I just did there. Here we go. And today is 10/19. It's Thursday evening. Okay. Leave some room for our margin questions. We're doing our Cornell notes. And if we look over here, the main question that we want to answer here is what is meant by the dual nature of light? What is meant by the dual means two, right? The dual nature of light. Question mark, okay? So if we look over here at our text here, the subtitle here, using photons to describe light. So there is quickly it became apparent that the models that science had been using to explain the world on a large scale level, Newtonian physics, that kind of thing, were not adequate when it came to explaining things at the atomic level. As it says here, as quantum theory was developing, it became clear that nature appears to behave differently at the atomic level. Okay, this was kind of a source of conflict. And so this conflict, it says, forced physicists to find new ways of describing natural phenomena. And that happens, right? As we learn more things, our explanations sometimes have to be modified. Okay. The phenomena of light, which is fundamental to the study of atomic structure, is one of those examples. Okay, so this conflict forced physicists to find new ways of describing natural phenomena. Okay, so Roman numeral 1 over here. Light and atomic structure were difficult to explain. In traditional terms. A new way was needed. Okay. If we come back over here, by the early 1900s, scientists understood that light is a form of electromagnetic radiation that has no mass and travels in waves. As good as this explanation was, let's go and underline that, okay? Yeah. By the early 1900s, scientists understood that light is a form of electromagnetic radiation. It has no mass and travels in waves. Okay. However, there were two exceptions. So this description worked, except there were two exceptions. Something called blackbody radiation and the photoelectric effect. Okay. Blackbody radiation and the photoelectric effect. Neither of these phenomena was explained by the wave mode of light generally accepted at the time. Okay, so capital A over here. In the early 1900s, light was understood to be a form of electromagnetic radiation. If you watch one of these videos, they'll go ahead and actually kind of draw a y-axis. They'll go ahead and draw an x-axis. This is y, this is x. And they'll show both the light traveling like this, and they may say that that is the electro, and they may say something like this, where the y, this is the blue, is the magnetic portion. Okay, electromagnetic radiation. So it kind of had two components to it. Two components. Okay. Now, let's put letter B here. This description worked pretty good, but it did not explain this explanation. Generally worked, but didn't explain two things. One was black body radiation, and it did not explain the photoelectric effect. Okay, so on the next paragraph here, it goes and explains black body radiation occurs when a metal emits different colors of light depending on the temperature to which it is heated. Okay. Metals emit different colors depending on the temperature they are heated to. Okay. And then the second one, the photoelectric effect, results when a metal emits electrons when exposed to light at certain frequencies. Certain frequencies. Okay, so here we're running into a problem here. This video is going to explain the photoelectric effect, but in general, the photoelectric effect, you can have your nucleus with neutrons and you can have your, we're just going to go ahead and use a simplified Bohr model here. You can have an electron that's sitting here, and when you have energy that strikes your electron, the electron can be completely ejected. Completely ejected. Not just jump up to one level and then return back to its ground state, but actually be kicked out, completely ejected or kicked out. Okay, and we call that the photoelectron. Okay, so as this electron gets kicked out, this electron called a photoelectron. Okay, and watch this video and they'll go and kind of explain that idea a little bit. Okay. In 1905, Albert Einstein used quantum concepts to describe the behavior of light. He expanded the description of light as a wave. So he argued that it wasn't just a wave, but it also, he hypothesized that, so he expanded the description as a wave, and he hypothesized that light behaves like a stream of particles. And he used the term photon to describe those particles. Okay, so let's go ahead here and let's call this letter C. Einstein proposed that light not only behaves like a wave, but also like particles. It says almost if he were saying that if this is your y-axis and this is your x-axis, and you were to go ahead and draw light as a wave, he was saying in essence that, oh, I didn't really want to do that. Not only was it a steady stream like that, but it also, let me see, undo that. How can I erase that? Erase partial strokes. That's what he said. It actually was behaving like packets of energy. And these packets of energy were photons. Packets of energy. Photons. Okay. It's almost as if they were like little waves of energy, right? Okay. And this is what we call the dual nature of light. Okay, this is referred to as the dual nature of light. Let's go ahead and pick a little darker color here. The dual nature of light behaves as particles and it behaves as waves. Okay. This is what we call the dual nature. By combining the concept of quanta and Einstein's description of the particle behavior of light, physicists now describe light as having, so here we go. Physicists now describe light as having a dual nature. Light has properties and behaviors that make it act like both a particle and a wave. Okay,